Hi everyone. In this video, I am going to solve a problem on mechanical translation system. Here is the problem. Write the differential equations governing mechanical system shown in figure and determine the transfer function. So here we have the mechanical translation system diagram. In this, we have the two mass elements M1 and M2. We have the different elements apply the forces on masses. From this diagram, we need to be find the transfer function. That is x of s by f of s, that is output divided by input of with respect to Laplace transform. So first we need to be identify that which one is input and which one is output. So in the system, the applied force f of t is an input and displacement x is an output. So Laplace transform of f of t is equals to f of s. So already we know, right? The time domain function is converting to s domain. It's need to be apply the Laplace transform on the time domain function. Similarly, Laplace transform of x1 of t equals to capital X1 of s. Laplace transform of x of t is capital X of s. So from the transfer function definition, we can get capital X of s by f of s. Already we know, right? The definition of transfer function, the ratio of Laplace transform of output divided by Laplace transform of input. Now, the system has two nodes and they are masses M1 and M2. The differential equations governing the system are given by the force balance equation at these nodes. Here, the force balance equation we can append by Newton's second law. That is, sum of applied forces is equals to sum of opposing forces. So we are going to be applying the transfer function by solving this mechanical transition system in two cases. We have to make the differential equations for both mass elements M1 and M2. We see that of case 1, the free body diagram of mass M1 is shown in figure. So this is the free body diagram and the opposing forces acting on mass M1 are marked as Fm1, Fk1, Fb1, Fb and Fk. So here it has a 5 opposing forces acting on M1. So let me see how we can get these forces are acting opposing to the mass. So see here, this is the mass element M1, uh, K1. So one the respect to with respect to their mass itself act as a opposing force, and B1, that is the friction element, B, that is also dashpot friction element, K and K. So totally four opposing forces acting on M1. Now we'll see that differential equation representation of these five forces. We can represent F1 is equals to m1 into d square x1 by dt square, because x1 is the displacement with respect to the mass 1. Fk1 is equals to k1 x1. Fb1 is equals to b1 into dx1 by dt. Fb is equals to b into d by dt x1 minus x. Fk equals to k into x1 minus x. So here B element and K element is common for both nodes, that is both mass elements. That's why it will experience that both differences of displacement. So as we know, the by Newton's second law, sum of applied forces is equals to sum of opposing forces. So here the mass element M1 doesn't have any applied force. That's why we have to keep it 0, and remaining opposing forces are add each other. We will substitute this differential formation for these five opposing forces. We will get that in this format, that is represented by the equation 1 is m1 d square x1 by dt square plus k1 x1 plus b1 dx1 by dt plus b d by dt x1 minus x plus k x1 minus x equals to 0. So here we found the differential equation for m1. Next step is we have to apply the Laplace transform, because the equation 1 reference which is in a time domain, so we have to bring it back to s domain. So it is only possible by the applying Laplace transform at with 0 initial conditions. So you'll see that after applying the Laplace transform to this equation, what we'll get. So this is the equation we'll get. If you apply the Laplace transform to the second order differential equation, you will get s square into x1 of s. So here the constant, right, k1 x1 of s plus here first order differential equation will get s Next, here also first order differential equation bs into x1 of s minus x of s plus k into x1 of s minus x of s. So here we got the equation after applied that Laplace transform to the differential equation in time domain. Now, what we had to do means we had to be bring x1 of s all the terms x1 of s all the terms one side and x of s terms one side. So finally, we get that equation two, that is x1 of s is equals to x of s into bs plus k divided by a1 s square plus b1 plus b into s plus k1 plus k. So this is the equation which is belongs to that mass element m1. Now we'll go to the mass element m2. So the free body diagram of mass element M2 is shown in figure. The opposing forces acting on mass M2 are marked as Fm2, Fb2, Fb, Fk. So let me see that mass element M2 having that how many opposing forces and what are they created. So here this is the mass element, right? So this is the mass element M2 and it having that one applied force F of t and its mass itself makes that opposing its direction and one is second one is friction created by the dashpot, third one is friction created by spring element and one is b2. So total we have 1 2 3 4, so four opposing forces acting on uh, mass element m2. We'll see that differential form of all forces. We have the four opposing forces. Here, Fm2 we can represent m2 into d square x by dt square. Fbt is equals to b2 into dx by dt. Fb is equals to b d by dt x1 x minus x1 and fk equals to k into x minus x1. So here, these two elements is common for both m1 and m2, right? So that's why it is experienced that both displacements already we seen in case one. Now we have to form the equation by using Newton's second law, that is sum of opposing forces is equals to sum of applied forces. So we have the applied force on m2, that is represented by f of t, and we have the four opposing forces or Fm2, Fb2, Fb, and Fk. We'll substitute these four differential equations in this Newton's second law. We'll get equation 3, that is m2 d square x by dt square plus b2 into dx by dt plus b into d by dt into x minus x1 plus k into x minus x1 equals to f of t. Now, this equation is in time domain, so we have to be convert this S domain by applying the Laplace transform. So, on taking Laplace transform to the above equation with zero initial conditions, we'll get m2 s square x of s. So here s square you got for the second order differential equation. If it is first order differential equation, we will get s. For constant, just we can get that the coefficient k into x of s minus x1 of s. So this is the equation we got after apply that Laplace transform to the equation 3. Again, we have to be bring one group to x of s, one group x1 of s, one group. Finally, we got that equation 4, that is x of s into m2 s square plus b2 plus b into s plus k minus x1 of s into bs plus k equals to f of s. Now, by using equation 2 and 4, so already we found the equation 2 by solving that mass element m1, right? So that equation that is given by x in terms of x1 of s is equals to x of s something. So that equation we have to substitute in this equation 4. The reason is finally we have to be represent the equation in terms of f of s and x of s. We have to eliminate that x1 of s term because we need to be find the transfer function that is given by x of s by f of s. So that's why we have to be eliminate this x1 of s term. That's why I'm going to substitute equation 2 in equation 4. So here instead in the place of x1 of s, I'm going to be substitute this all the term, this term. If you substitute this term, the equation becomes like this. Now, both terms having the common element x of s. So let bring common for both the terms. X of s equals to m2s square plus b2 plus b into s plus k minus bs plus k whole square. So both are in numerator terms. So we have to be multiply that divided by m1s square plus b1 plus b into s plus k1 plus k equals to f of s. By solving this equation, that is, we have to do cross multiplication x of s into this term is multiplied here. Then you will get m2 s square plus b2 plus b into s plus k into m1 s square plus b1 plus b into s plus k1 plus k minus bs plus k whole square whole divided by m1 s square plus b1 plus b into s plus k1 plus k equals to f of s. So finally we got the transfer function x of s by f of s equals to m1 s square plus b1 plus b into s plus k1 plus k divided by m2 s square plus b2 plus bs plus k m1 s square plus b1 plus b into s plus k1 plus k minus bs plus k whole square. So this is the transfer function for the given mechanical translation system. So here, what is the main intention to convert that a physical system to differential equation means we have to be convert the system by using internal parameters. Whatever we can see the parameters in the transfer function, this is the internal parameters of system. So by using by changing the any parameter, we can control that that particular device. So that is the reason we have to be bring the a physical system or a control system in terms of transfer function, then only we can do modifications whatever we require to obtain the steady state condition like that. So this is about mechanical translation system, and thank you.